So quickly. So yeah, the idea is just that you have some function that makes use of field Apox. There's some Apox prime field. Yeah. Huh? Yeah. Some Apox prime field, right? Then you want to now track how many operations you did over this computation. So that's what you use the field tracker for. So the way you just do is you just add. Can you guys see?
Yeah.
Is it better? So you just add the link as a dependency. Then let's just write some computation. Let's just say this adds two numbers and returns a field. Right? So that this computation is supposed to just add two things. So just one addition. That's all right. Now let's say I wanted to track that. Let me just write a test. So let me just print it out. Do I have ActiveF? Makes sense? So this just calls compute. Then we can test this. So we can see the answer, right? 12. So we know the computation is working. So if you wanted to now replace this, so you know what we do is that we just wrap the field element, but then we now track under the hood. So all you just need to do is just import the wrapper. So that's ft. Okay? Then you just need to wrap the type. So you can create another type called fr so that you don't need to change your code. Now this fr is going to be equal to ft wrapping bn254 fr. Now you don't need this other fr again because we can just use our own fr. So the code still works, right? Like you still get 12.
Yeah.
But you can now see that 12 is inner.
Yeah.
Okay, so that means I've been wrapped. But the answer is still correct. But now the cool thing about this now is that you can do something like print summary, right? If you call this, you're basically going to see that, okay, you just have one addition. So it's as simple as that. So all you just need to do is like, wherever you're writing your test, you just wrap, it doesn't have to be your test, you just wrap it with ft, whatever your field type is. And then you don't need to change anything in your code again. Like, it just works. Then you can just like print summary whenever you're done with your computation.
Okay, so this just happens like in the test, right?
It can happen anywhere, actually, yeah. But preferably in the test. Yeah.
Then why are there squiggly lines? Right?
That's just Rust Rover. Don't mind. Because it works, it runs, so it's just Rust Rover. So let's use something more complicated. Let's use our repo.
You said you can put the enemy, can also be inside our code,
Yeah, it could be, but preferably just do inside. You know, your code doesn't actually use like any concrete field elements, right? Like it's just like traits. So when you actually want to run it with something concrete, preferably you're doing that inside your test, or maybe your main function, right? So you can put it anywhere you have like the concrete. So anytime you're supposed to pass in a concrete fr, you can pass in the wrapped fr or fq or whatever.
So what are we adding in the dependency?
So you just add
Wow.
yeah, it's a GitHub link.
When you get that,
I'll send it to you, don't worry.
This is not bad.
It's recording. Okay, so let's do something more complicated because this one is too. Let's use our implementation of multilinear.
This is your GKR.
I've updated my GKR. I did it a while ago. I want to redo it, but I will have like more
So you have this
crazy
inside, but
ideas.
really inside.
No, not from, not visually.
So
Like I've read, we read Vego plus plus, we read Libra, so like there are new things there that I want to like kind of like
yeah, you
refine.
don't need to delete the other one. You just leave it and then.
There's always commit history, so you can always go backwards and why not that I will not put two implementation of GKR and say, oh, this was the old. No, I'll just delete it. But yeah, huh?
GKR anyway.
Francis is doing that, so you can always go on this one. Okay, so this was our implementation of multilinear. This is our implementation of sum check. Yes. Okay, so let's use this. Let me add this thing. So okay. So inside sum check, we still have our FR. Let's just run the test first, make sure that everything is working. For running tests. Why do I need internet to run my test? And I'm connected to the internet, so it's probably like VPN stuff. Okay, so it's working now, right? So now, what are we doing here? We have a multilinear polynomial. This is our famous multilinear polynomial, right? Then we are incoming. Yeah. So we have our polynomial, which is just like the 0, 0, 0, 3, 0, 0, 2, 5. And then we convert everything to field elements. Then we just run some check on this with 10 as the proof. And then this is the verified results, right? So now what we just do is that we just wrap it in. So it's like just use field tracker FT. Then we just add a new type. It's a macro, by the way. Then we can get rid of this guy. So now nothing changes, like everything just works. So if we run it again, it should still pass, hopefully. So some check is still passing, right? Now all we need to do is print the summary at the end of the completion. So now we should see, so just 48 additions. So polynomial is really small. So when you guys are testing, you guys should test something like really large. Maybe like a polynomial that has like 2 to the 20 elements. That's like a 20 variable polynomial or something. That's like standard. Currently in production system, the polynomials are usually that large. 2 to the 20 to the 25 or so. So it tells you the number of, it's just like a million plus elements. So like 2 to the 20 is 1M. It's not bad. Don't worry, your implementations can handle it. But now there was something else. So you might want to like scope stuff in terms of like, this one is just showing us all the global summary. But we might want to know, okay, how our partial evaluation now as part of the sum check or our rounds, how did each round of sum check contribute to this global summary, right? So you can now go into your code, select sum check prove now. This is how we're doing this for each round, right? So what we could do is that we could do something like start T scope, which we can just call like sum check round. And then at the end of the day, at the end of the round, we just end T scope, okay? So what this is do is to create a scope within your entire computation that is to now track this one specifically. That way you can see how much each round is contributing to the start. So if I run this again, we now see that I had like 3 sum check rounds. And then each round, you can see that the first round contributed the most. And that makes sense, right? Because sum check usually starts with something that's really large. Then every round is like halving that. So the beginning round like contributed like 19 additions and 12 subtractions, and the other one just 9, 6, and 4, 3. Make sense? Make sense? So that's really good. So you guys should just like,
So can I see the command again?
can you see what?
The command again. No, not the command.
This one?
Start.
See scope. Like trackable scope. They just like name it. Whatever you want.
Is it because it's in a for loop or something, or it does not matter?
No, it can be anywhere. Like any block of code that you want to track separately, you can just like wrap that block of code in this. Any questions? Okay. So that's it. So you guys should just
The
Start.
name inside, does it matter?
anything you want for your own like your ability to like know what that block is talking about. So you guys should
Sorry. That's summary. What's the command? Is it
print
just
summary. Print summary. Don't worry, you will see. Okay, I'm coming. Yeah, print summary. There's also just summary, right? Like if you there'll be no need for it per se, but you could just like get the summary out. But this one won't print it out. It will just store the summary in a variable that you can then use for. Because what we wanted to do was we wanted to like create a feedback loop where something will make a change, then that thing will get the summary to see how well it did. Then it's now use that to make it change again, and then it's just like this loop on and on like that. It's kind of like improving software, something like that. That was like the original reason why we did all these things. Because I wanted to create like a polynomial library that can work in any HC, right? Not just 2HC. So we wanted it to try rather than 2HC, not just 2HC. So we wanted it to try like different configurations to see which one will be best for the problem at hand. So it needs to know how well it did. Hence this. Then that feeds back into itself, and then it now uses that to know, okay, let me try a different configuration in this direction or something like that. Hypercube. So you know there's Boolean hypercube. That's 2HC. Yes, HC. Then there's like ternary hypercube and all this. Make sense? That's like rather than just 0, 1, 0, 1, 2. Or rather than just 0, 1, 2, 0, 1, 2, 3. So you can go as high as you want. Alright, so that's it.